Alright, so the system shown is in equilibrium. The maximum allowable force in cables AC and BC are 300 and 200. Alright, so we got that. The total force in the spring arrangement is 360 pounds. Okay. So I know that this parallel configuration of springs, the whole thing as a whole, provides a force of 360. And it is observed that spring 1 stretches 0.2 feet. 0.2. In addition, the normal force on the block is 331 pounds. So here I have this normal force, and it's 331. Alright, so let's start out with part A, the maximum allowable weight of block D. So I look at this block D here. We're going to have an unknown normal force, ND. We're going to have an unknown weight, WD. We're going to have an unknown tension here. Call that TD. We don't know anything. So, I have a limited time on this exam. I'm not going to waste my time drawing the free body diagram equations for this system right now, because there's just too many unknowns. I'm going to go to my next system and see if I can figure anything out, and my next system is here. The failure criteria in FBD at C. I want to maximize this weight. It says maximum allowable weight of block D. And I'm going to try to maximize that weight, D, so that I cause one of these tensions here to be at its maximum. Alright, so let's do the free body diagram here and dive into this. So here's my two ropes here so far, TAC and TBC. I have these angles here, 60 and 50. Of course, I want to define my X and Y axes. And I have one more tension here, the tension from this rope coming down from C. I'll just call this tension TF, and that is making a 20-degree angle with my negative y-axis. So even though I have these angles for TAC and TAB, I want to get angles from these force vectors and my x or y axes. I need something like this. That's really how you get the direction for a vector. So if I extend my x-axis here, I know that my 60 will be here, and my 50 will be right here. You can thank geometry for that one. And I'm good with this 20 right here. That 20-degree angle is between my negative y-axis and my vector, so I have a nice direction vector for that TF. So I'll start with summing up the x components of my three forces. So I'll have TAC cosine of 60. That's going in the negative x direction. I'll have a TF sine of 20, also going in the negative x direction. And I'll have TBC cosine of 50, and that one's actually going in the positive x direction. Alright, got that? For my sum forces y, I have TAC sine of 60. That's going to be going the positive y. TBC sine of 50. It's also going to be a positive y component. And TF cosine of 20 going in the negative y direction. So, again, I want to maximize the weight of this block. And the bigger the weight of that block is, the bigger the tensions will be here and here. You know, ideally, both cables could be operating at their maximum capacity, 300 and 200. But probably not going to happen. I bet you only one will be able to be operating at its max. So what we're going to do is we're going to plug in 300 for TAC and then see what TF and TB are. So again, we'll plug in 300 right in for TAC. Let's assume that this is the lucky guy, the lucky rope that gets to be operating at maximum. And we'll do that math, and we'll solve for TF and TBC. So if we do that math, I'll get 672 for TBC and 824.2 pounds for TF. So clearly this is not possible because TBC can only hold up to 200 pounds. So I know that this is not the reality. This is not what is actually going on. So let's try it the other way. Let's assume that TBC can be operating at its maximum. So we'll plug in 200 for TBC, which turns this system of equations into two unknowns and two equations, which we can solve. Either, brute force on algebra, or I just like putting everything into a matrix. And we can figure out what these two unknowns are. So let's crunch the math there. We'll get 89.3 pounds for TAC and 245.3 pounds for TF. So, looking at that other cable, TAC, we see that it is well below its maximum limit. And of course, TF has no limit given in the problem. So we know that this is the reality of the situation. Alright, so now that we know the tension in this rope, notice that this rope extends all the way over here. So I might do a free body diagram on this pulley right here, so maybe we can figure out the force of the rope attaching to block D. So that's actually pretty trivial. We have 245 in this rope going up and 245 here, so that's two 245.3s going up diagonally in the same direction. And for there to be balance, there must be 490.6 pounds going downwards to the left. That's just 245.3 times 2 to get that 490.6. So I know this force right here, 490.6. Alright, perhaps now I can do that free body diagram at D and figure out some stuff. So here's my block D right here. I can just treat it like a particle. I'll have a force going downwards, that's the weight of D. We'll have the tension from that rope going up the ramp at 490.6 pounds. And we'll also have the normal force pushing up from the ground on B. And for my coordinate system, I'll choose this to be my X and this to be my Y. It's usually a good idea when you're on a ramp to tilt your coordinate system, because as you can see, two of our forces don't even need to be split into components. This one's only a Y, this one's only an X. So no need for an angle for these two vectors. We already have their directions. We need an angle for this one. Here's a horizontal line right here, which means this is 30 degrees. 30 degrees here and here. I'm going to split this weight vector into two components. Y, it's going to be a negative Y here, and this will be a negative X. Note that this whole thing is 90, which means this is 60, and from here to here is 90, which means this right here is back to 30 degrees. So that 30 degrees is good because that's the angle between our weight vector and my negative y-axis, this line right here. So now let's do some of the forces in the x direction. So I just realized that I drew my force vectors in red. Usually I try to draw them in green, so I apologize for the confusion there. Alright, so we have a plus 490 in the x direction, and we have a minus the weight times the sine of 30 to get us the x component, and that is in the negative x direction. And the normal force of B here is not in the x direction, so that won't appear here. So in the y direction, we have just NB, because it's just going up in the positive y direction, and we have a minus WD times the cosine of 30. WD cosine of 30 will be this component of our weight vector. It's in the negative y direction. So we can solve our sum forces x equation for the weight of block D, no problem. That'll be 981.2 pounds. And note that this will be the maximum allowable weight. Why? Because in the very beginning, we stipulated that our configuration of ropes here was pulling the max possible tension that it could. We couldn't maximize AC, but we maximized BC. So our weight D is just heavy enough such that BC is just about to break, really. Any more weight here and BC would be above its 200 limit. So this number here is truly the maximum weight that we can put in that block D. Of course, we can take that 981.2, plug that right in here, and figure out our normal force on B. Oh, and that just so happens to be our next question here. And we'll get 849.74 pounds. So here's our weight D and our normal force on D. And I just realized I've been calling normal force B this entire time. Goodness gracious. That is my bad. Of course, it's the normal force on D. Let's pretend that never happened. Alright, part C, weight of block E. Here's block E right here. Looks like we're going to have to work our way through these tensions. So here's our 245.3 rope. All points on this rope are at 245.3 pounds. And it just keeps going, as you can see. Well, we can do a quick FBD on this pulley right here. Here's our pulley. We have 245.3 going in and out. So that's two of these 245.3 forces. What force do we have going downwards? Well, that is the weight of block E. And of course, we didn't have to do any sum forces crazy math here. This just must equal the sum of these two for there to be force balance. 245.3 times 2, 490.6 again, pounds. So now for part D, tension at G. All right, well, here's G. I'm assuming they mean the tension of this rope right here. Alright, so we were just over here. So here again is that 245.3 going and going and going and going and going. Okay, here we go. So all this is at that 245.3. I can do a quick FBD at that pulley. And we learn that the force going downwards must be both of these added. The 490.6 again. Alright, looks like we have enough information to do an FBD on this 150-pound block. So I have 150 pounds going downwards. I also have this other rope right here pulling downwards. And actually, you can see this rope extends through that pulley all the way to G. It's all the same rope. Therefore, it's all the same tension. This is TG, the tension at G. Actually, what we're looking for. Then we have the rope to the right on top of the block. That's our green rope. That is the 245.3. And then we got this yellow rope right here, the 490.6. So if I do a quick sum forces in the Y, 490.6 going up, 245.3 going up, a TG going down, 150 going down. If you do that math, you'll get 586 pounds, or the tension in that blue rope, which is the tension at G. Alright, now for part E, the weight of block J. So let's zoom over to J here and see what we got. I know I have a normal force right here. I actually think I lost that number for it. Yeah, the normal force on J is 331. I don't know where that went. So 331. What else do we know? Well, we know the total force from this parallel spring system. So I know what that means is that all in all, it feels like one big force is tugging the block downwards, and that force is 360. How do I know that this force is tugging the block down the ramp? Well, it says that spring 1 stretches. So if spring 1 stretches, that means all of them are stretching, because I know springs in parallel all move with the same x. So if these springs are stretching, if these springs are in a stretched configuration, they're wanting to pull that J down. Alright, so these are two known so far, the 331 and the 360. That's good. Alright, what else? What other forces do we have on J? Well, we have the weight, of course. That's going to be an unknown, WJ. And we have this tension here. We can call that TJ for the tension of J. And it doesn't say there's friction, so let's assume frictionless. And I think that's everything that's touching that block J, which means we only have two unknowns here, and I have two equations with which to analyze this block. I have sum of the forces in the x is equal to 0, and sum of the forces y. So with two equations, we can solve for our two unknowns. So writing out all the FBD equations and everything is worthwhile here. We'll actually be able to calculate these numbers. So here's my ramp here. I know that is inclined at 25 degrees. Here's my block J, which I'm just treating like a particle. So here's my free body diagram. Of course, we know the normal force on this block here is 331 pounds. Alright, so we're tilted here, so I'm going to tilt my coordinate system. I'm going to make x go this way and y go this way. And that's great because this is completely in the negative x, completely in the positive x, completely in the positive y. We really just need to find an angle for our weight vector. So I'll extend my negative y-axis here. Let me just split this weight vector into components. Here is the y component, it's going to be negative. And here is the x component, that's going to be positive. And that's a right angle right here. I'll draw just an imaginary horizontal line here so I can identify my 25 degrees. I have a 90 right here. So this has to be 65 degrees. And I have another 90 in between these two. So this has to be back to 25 degrees. Alright, so let's do the sum of the forces in the x. We have a TJ going in the negative x direction, a 360 from that total spring system, positive x direction, and the x component of our weight in the positive x. And in the y, we have 331 going up in the y from our normal force, and the y component of our weight is obtained using the cosine. So we can solve for the weight of J using our sum forces y equation. And of course, it's not the weight of D, it's the weight of J. My apologies again for here as well. We'll get 365.2 pounds for the weight of block J. We can of course put that right in here and solve for the tension of that rope, TJ, and we'll get 514.35 pounds. So there is the weight of block J. So now for part F, the moment at H. Here's point H right here. So we will do a free body diagram on this rod. So I have two forces on this rod here. One is that tension at G that we've already discussed, the 586. And the other is this tension coming off the block J, and that's this 514. And they want the moment at H. And here's how I think through what this means. Actually, there's a fourth force acting on this object. I mean, isn't the ground affecting this rod? And for sure it is. The ground is touching this rod, so therefore this ground, this weld point where we're welding in the rod to the ground or whatever, must have some effect on this rod. So this ground, since it's touching the rod at this point, it'll put some force on the rod. And this force will have some x and some y component. And I'll just assume it to be up and to the right. So hy and hx, the two components of the single force that the ground is putting on the rod at point H. Now also, if you look at our diagram, if you look at that point H, you can tell that this is what we call a fixed support. It's not like a hinge. It's not free to swivel. It's not free to rotate about H. It's rigidly welded in, it looks like. What that means is that the ground at H also puts a couple moment on the system as well, which we'll call the moment at H. This is the moment that the ground provides on the rod so that these two forces are not able to rotate the rod about H. So in my mind, this is what the question is asking for, the moment at H. And to figure this out, we'll want to sum up all of the moments about point H here. And why are we summing the moments about point H? Well, these two forces are unknown, and that's not good. If we sum up all of our moments about this point H right here, these two forces, or these two force components, will create a zero moment about this point because they're going right through that point H. And therefore they will not appear in this equation that we're about to write. Which is good for us because, again, they're just two more nodes that we do not want to deal with. So that's why we're summing the moments about point H. Alright, so sum of the moments about H is equal to 0, of course. And I'll say that the counterclockwise direction is positive. Alright, so let's calculate the moment of this force about point H. And since we're in 2D, I'm going to use our simple scalar version method for calculating moment. The force times the lever arm. Now we could do this. here's the line of action of that 586 force, and here is the lever arm. By definition, it's that perpendicular distance from the line of action of the force to my point. But that would require me drawing a big right triangle and doing some geometry, and that's annoying, so I don't want to do that. So here's how I'm going to calculate the moment of this 586. So the 586 is going to have two components. It's going to have this x component and it's going to have this y component. So let's pretend that these two forces act at this point instead of this one. Remember, these two are the components. They together create this force. So these two forces will really act the same way as the resultant does. It's kind of going back to that idea of equivalency. So I'm going to calculate the moment of these two force components, add them up, and that is the moment of the main force. This is called the principle of moments. So the moment of this component will actually be 0 because its line of action passes through point H. So that's easy. And the moment of our horizontal component will simply equal that force times the lever arm distance d, which is clearly this distance right here. So that horizontal force component will be 586 cosine 55. And that distance will be the 3 feet plus the 3 feet to make a total of 6 feet. The direction, this force will want to spin this object counterclockwise about h. So I'm going to give this whole thing a positive sign. And that's it. This is the moment of this force about this point. Same exact approach for this one. I split this force into its two components. It's x and it's y. And I'm going to calculate the moment of these two components and then add them. The moment of this component about h is going to be 0 again because that line of action passes straight through h. That force will not be able to rotate about h at all. Imagine pushing downwards on that bar. That's not going to help it rotate about h. And the moment of this component is just going to equal its force, which we'll calculate in a second, times its moment arm, which will be this distance right here, just 3. So the force, 514.35 cosine of 25 degrees. And the lever arm would be just 3 feet. And we can see that this force will want to rotate this object clockwise about h, and clockwise is in the negative direction. Like we discussed, these two force components, hx and hy, don't create any moment about point h. And finally we have mh, the couple moment that the ground provides on the system. And I'm assuming that couple moment to be in the counterclockwise direction, so it's going to be a plus mh. And the sum of all these moments, of course, is equal to 0. So I can, of course, solve for the moment at h. And if I do that, we'll get a negative 618.2 pounds times feet. Now remember, if our math gives us a negative sign, that means our assumption was incorrect. And my assumption was that this moment direction is in the counterclockwise. So clearly it's the opposite. This couple moment is actually acting in the clockwise direction. So the moment at h will equal 618.2 pound-feet, and I'll put a little arrow this way to show the direction. And last but not least, part G, we want the spring constant the stiffness of spring 3. So, this is really all about knowing the ins and outs of equivalent springs. Springs in series and parallel, and knowing the whole derivation and the whole story that's going on there. And because I've derived those series parallel spring equations, I can really step through this problem with minimal difficulty. So the total force in the spring arrangement is 360. I know that when you have springs in parallel, each one of their forces add together to make the total force, the force of that equivalent spring. And that total force is 360 pounds. So that is the sum of the force in spring 1, spring 2, and spring 3. I, of course, can write in Hooke's law for each one of these forces. And let's substitute in the stuff we know. K1, that's 300. X1, do I know the stretch in spring 1? Well, do I know the stretch in any of the springs? Because remember, when the system stretches or compresses, each spring moves with the same x. And I actually do. Again, from our initial information, spring 1 stretches 0.2 feet, so that's actually the stretch in all the springs. 0.2 for x1, 0.2 for x2, and 0.2 for x3. Alright. K2 we know to be 500. And K3 is the thing we want to know. And of course, all this is equal to that 360. So it looks like I have a nice equation that is all set up for me. And I just have to use it to solve for the stiffness of spring 3. So again, my recommendation: derive those series and parallel spring equations for yourself. Walk through the steps. Talk it over with yourself. Because if you know the ins and outs of that, that story, that derivation, you can easily step through these tricky spring scenarios that they're going to throw at you on these exams. And we'll get K3 as 1,000 pounds per feet. Pounds per feet. Pounds per foot. And there is our final answer right there. Alright, these exam problems are crazy, no doubt about it. Please ask me any questions if you have them. Leave them in the comments, and I will do my best to answer.